So in machine learning, we so whether we're talking about a supervised learning system or the reinforcement learning system with cost and reward functions respectively, in either of those cases, we use backpropagation in order to adjust our model weights up and down the deep learning system. And so, is there a kind of biological analog of backpropagation? It seems to be a question that has sparked a lot of debate in the neuroscience community.
Yeah, it has. And I ultimately am, for better or for worse, associated with one fairly, let's say, extreme position on that question, which is yes, I think the brain has some kind of approximation to backpropagation. Now, let me explain why I say that. This comes back to the question of credit assignment and the sort of general principles that systems will have to solve. So when you look at a parallel distributed computer and you're trying to figure out how to train it in a way that it gets better at the particular tasks that you've given it, i.e., better at minimizing the loss or maximizing the rewards that you've given it, it's very hard to know how to change your system. All of those billions of individual units that are acting in parallel, it's very hard to know what to change in that system because it's all interconnected. It's this huge gigantic network where everything kind of depends on everything else. And so figuring out why did we get an error here can be very challenging. Now, it just so happens that we have a really nice solution in AI, and that is backpropagation. Backpropagation solves that problem for us. It tells us, okay, here was the set of synapses that were really kind of responsible for this error. If you change them, you're going to reduce your error.
Yeah, and really quickly there, a synapse is where two neurons, where two brain cells connect with each other.
Yes, exactly, exactly. So we sometimes refer to the connections between units in artificial neural networks as synapses, or at least as synaptic weights. And what backprop does is it gives you a rule for updating the synaptic weights in your artificial neural network in order to guarantee that your loss will go down over time or your rewards will increase over time. Now, the thing that I always come to is that the brain faces this same problem. The brain is a parallel distributed processing system. It has to somehow solve the problem of figuring out which of the synapses and neurons were responsible for the errors or the successes. So I think most neuroscientists, though not all, and this is something that bugs me sometimes, but let's just say the vast majority of neuroscientists will recognize this as a real problem. We'll say, yes, indeed, the brain has to somehow figure out what physiological changes are going to actually help an animal to get better at something in some way. The question then becomes, is there any chance that the brain's solution to this problem bears any resemblance to backpropagation whatsoever? And that then is less of a sort of base assumption and more an empirical question that we can try to address. The reason that I come down on the side of saying that the brain probably does have something kind of like backprop, or at least kind of like gradient descent, which is what backprop is. It's a version of gradient descent. And we can go over what that is if you want. Just let me know.
Yeah, I think I guess we can kind of really quickly, it's like, so gradient descent is something that is common to a lot of machine learning algorithms, and backpropagation is like, I don't know if the right word is like extension of that or like specific case of that
That's right.
to neural networks where uh, we need to be doing something special. And it's exactly what you're about to describe in the biological system, where because the artificial neural network almost all, unless it's an extremely shallow neural network, like if it's a deep learning network, then it has many layers of artificial neurons. And so this gradient descent, it's a special case of it because we need to be updating the model weights, the synaptic weights, across all of those layers. Yeah, so I think that's probably a good enough explanation for.
Okay, great. So I mean, I think maybe though, to actually, I'm realizing I should unpack it a little bit more for what I'm about to say. So the way that gradient descent works is it works according to the following principle. So let's say you've got some loss function that's measuring how badly you're doing at your task. It's measuring, say, your error. Gradient descent as a principle says, okay, the way that you're going to get better at this task is you're going to look at the slope of that loss function. So you're going to look at which direction in your synaptic weight space, in which direction does the error get lower, and in which direction does the error get higher. Whatever direction the error is going lower in, we're going to follow that direction. That's how gradient descent works. And it guarantees that your error is going to go down over time because you're always updating your synaptic connections in a manner that is following that hill of your loss function. Backpropagation, as you said, is just one specific way of doing gradient descent in multi-layered artificial neural networks. What I really believe is not that the brain does backprop per se, but that the brain does some form of gradient descent. Now, why do I say that? I say that for two reasons. The first is that mathematically speaking, and this is a point that is sometimes not always well received and not always easy to understand, but I'm going to try my best to articulate it to you. Mathematically speaking, if your system is making small changes to itself, then necessarily, if you're getting better at the task over time, you have to be going down that hill. You can't be getting better at the task while making small steps if you're not going down that loss function hill. Like, it's just a mathematical guarantee. You have to be going down the hill. And so then the question is, well, maybe the brain's going down the hill not because it's actually figuring out the slope of the hill and following that slope, but maybe it's doing something else. Like maybe it's somehow got some way of randomly exploring the space. And if things get better, it keeps going in that direction. And if things get worse, it doesn't go in that direction. For example, that could be a solution that doesn't involve an explicit calculation of which direction the hill is going down in. What we've seen in AI, and this brings me to my second reason. So we know that the brain has to be doing, at least following the slope. And then the question is it actually actively calculating the slope? Or is it just that what it does happens to bring you down the slope? I think it actively calculates the slope. And the reason I say that is because one of the fascinating things that we see when it comes to optimizing parallel distributed processing systems is that most algorithms for solving this credit assignment problem, for guaranteeing that you're going down the slope of your loss function, most of these algorithms get worse as the network gets larger. It gets harder and harder, it takes more time to train your system, etc. For example, that approach I just described of randomly trying stuff and then keeping what works and discarding what doesn't work, that just gets totally garbage when you get to really large networks. And it's because it's just too much space to explore. If you've got, a billion synapses, you can't just randomly try different perturbations of those synapses and hope that some of them work. You've got way too much space to explore for that. So what we see is that most of the algorithms that people develop don't scale well. They actually get worse as the networks get bigger. The one exception is gradient descent. Gradient descent is fascinating because it gets better the bigger the network gets. And the reason for that is that gradient descent is following this hill down. Well, I should say, we don't fully know all the reasons for it, but one of the reasons for it is gradient descent is following this hill down. And a problem that gradient descent can encounter is that as it's following the hill down, if it gets to the bottom of a hill, it will stay there because it'll say, okay, I've got no more slope to follow, we're at the bottom. But you could reach what's called a local minima, i.e., you could reach, say, just like a tiny little ditch on the top of your mountain. So you're actually doing terrible, but because it just so happens that all around you the slope is going up, you're going to stay where you are. And for a long time, researchers thought that this is why gradient descent was a terrible algorithm and you shouldn't use it. And when I was a student in the late 1990s, that's exactly what I learned in AI class. You don't want to use gradient descent. You
Wow.
get stuck in local minima, it's garbage.
Oh, wow.
But as you add more dimensions, as you increase the space, the dimensionality of the space that you're exploring, now the chances that every single dimension is at a local minima
Oh
turns
yeah.
to an evaporatingly small probability. And
Right.
the vast majority of the time, you will never encounter a local minima unless you're very close to the actual true minima of your problem. Now, there can be points that are called saddle points, where you've got a minima in one dimension but not in the other, and they can be harder to escape, but there are tricks for escaping those. And so what we've discovered is that if you've got your tricks for escaping saddle points, then gradient descent just works better and better and better the more dimensions you add, because you reduce the number of local minima that might be bad, and the system just converges on beautiful solutions. So we have this issue that, solving the credit assignment problem, figuring out which synapses to change is challenging in a parallel distributed processing system. Most algorithms suck the larger your network gets, but for one, which is gradient descent. And what we see in brains is that there has been an apparent evolutionary pressure to increase the size of brains in mammals. Humans have stupidly large brains. Like, it's worth being explicit about that. When I say stupidly large, I really do mean that literally, because our brains take an inordinate amount of energy. So, like, our energy budget is, I think, like 20% of it is expended just on keeping our brain alive. And then when we're thinking, that increases even further. So we're spending some stupid amount of money, well, not money, energy on this one organ.
I guess money too.
Money too.
Burning that
Exactly.
money to fuel the neuron factory.
That's right, exactly. So we're burning a stupid amount of energy, and it also makes human birth a nightmare, right? Like, it's funny watching other animals give birth, and it's like a piece of cake. And then, if you've ever witnessed a human birth, you're like, it's not a piece of cake. And the reason is simply because of the size of the baby's heads, right? So, like, if you were just thinking about the survival of the human race, the most obvious thing to do would be to decrease the brain size, because, like, why do you want to have all this energy expenditure and horrible births? But if there's some reason that bigger brains helps you, that's why, right? Now, bigger brains are only going to help you if you can do something with them. So I think it's safe to say that whatever learning algorithm our brains have scales well. It works well with more neurons. And I think that's clear from the way that evolution has favored larger brains. But that being said, then there's the question of, well, what if there's another algorithm other than gradient descent that scales well? And so this is where I think that there are, I will place my careful scientist hat on and say, we don't know that the brain is approximating gradient descent, but I think it's a very viable hypothesis, because it is this algorithm that scales well with size, and we see an evolutionary pressure for size. Moreover, when we train artificial neural networks with gradient descent, they develop features that look a lot like what we see in the brain. And as a final thing, and this is part of what my lab's done, there's now lots of scientific evidence showing that there are mechanisms in place in the brain that could make gradient descent possible. So even though it sounds outlandish to some ears, there are literal physiological mechanisms that we have proven could be used to do gradient descent. Now, we don't yet have the experimental data to verify that the brain is doing gradient descent. That's TBD, but I am bullish on this question. I think we know that the mechanisms are in place that the brain could do it. We know that brains have representations that look like what you get out of gradient descent. And we know that gradient descent is the one algorithm we've discovered so far that scales well with size. Add it all up, I'm willing to say I put more money on the brain does something like gradient descent pot than the brain doesn't do gradient descent pot.
Nicely said. Yeah, nicely said. I'm in. I'm in.
Good.
Give me show me what betting shop I can put all my money down in on right now.